most atoms when bonding do try and obey the octet rule. For every good rule, there are some good exceptions. For this one, there are only 3 classifications of exceptions. So usually it's going to occur with boron and elements of higher periods of the periodic table, so at least on the 3rd energy level or greater. Here's one that
Miss
does
Dolby,
violate
please
the
call the office.
octet rule.
Miss Dolby, please call the office.
This one also violates the octet rule. BF3 is going to violate the octet rule by having access to less than 8, and SF4 is an expanded octet and will have access to more than 8 valence electrons, or at least that central atom. Let's look at boron trifluoride. So if we are dealing with the compound BF3, what we have here with our number of electrons, and let's just look at half for my number of electrons. I have boron and fluorine. Boron has 3 valence electrons. Fluorine has 7, and in this particular compound, I do have 3 of those. So if I look at my total number of electrons, I've got 21 plus 3, so that's 24. Half divided by 2 is going to give me the number of electron pairs that I have to deal with. So what I'm going to do is take boron, and I'm going to bond it to the 3 fluorines, because these do make a molecule, and I need to link them all together. So I have 3 electron pairs taken up by the bonds, and so that leaves me with 9 electron pairs left to work with. So I start putting them on the outside electrons, or outside atoms first, and fill up their octets. So fluorine already has access to 2, and I'm going to start right here. And so I need to put 3 more sets of electrons, and that's just 1 there. This fluorine would also need a full octet, and this fluorine needs an octet. So now I've used up 9 electron pairs, so that takes care of all of that. No electrons on that center atom. But if we look at that center atom, boron has access to only 2, 4, 6 electrons. That is okay. I say boron is a little guy, and he's one of the exceptions. If you see boron or beryllium, you need to watch out for a electron deficient or violating the octet rule by having access to less than 8. Alright, so beryllium and boron often do not achieve an octet, so watch out for those guys. They have less than an octet. They're electron deficient molecules. Here's one, SF4. I already talked about this one having an expanded octet. Sometimes you don't know that just by looking at them, but what will happen is that happy half will blow up. And here's what this is going to look like. So if I go to write the Lewis structure for SF4, I do happy half and sulfur and fluorine. To make each atom happy, sulfur would want 8, and each of my fluorines, and I do have 4 of them, will also want to have 8. And so that gives me a total of 40 electrons that they're going to want to have. Sulfur has 6, and a halogen has 7. And so what we're dealing with here is 34 electrons. 28. Yes, 34 electrons. All right. So happy minus half, I have 6 divided by 2, tells me the number of bonds, and that's 3 bonds. And here already I see a problem. Sulfur has to link with 4 other fluorines, and that's not possible with 3 bonds. When you run into a situation like that, that's what I call happy half blowing up, what you're going to need to do is just deal with half. Deal with the half and talk about half divided by 2. That's going to give me 17 electron pairs. And we'll just go ahead and draw this structure out. So I have sulfur in the middle because it's the first one written, and it's going to be bonded to 4 fluorines. Now, I have 4 bonds, So we'll go ahead and subtract those out of the electron pair pool. So I have 13 more electron pairs to deal with. Let's go ahead and fill up fluorine. They're going to want an octet. So I'm going to add 3 pairs to each fluorine for a total of 12 electron pairs that I was dealing with there. That leaves me one more electron pair that I have to deal with. None of the outside atoms can take it, so it has to go on that middle atom. And this is the Lewis structure for sulfur tetrafluoride. You'll notice that sulfur does have an expanded octet. It has access to 2, 4, 6, 8, 10 electron pairs, and that's the definition of an expanded octet. All right, SF6 would be another example of an expanded octet, and that one you could even see just from looking at the actual formula. For sulfur to be bonded to 6 fluorines, that's already giving it access to 12 electrons. The key is, and a lot of times on the AP exam you are tested on this particular fact, the only elements that can have an expanded octet have to have at least 3 energy levels. Now you can use the periodic table to help you remember which elements those are. Remember that the period numbers tell you how many energy levels something has. So it has to be on the 3rd row, 4th row, 5th row, 6th row, 7th row. You can never have an expanded octet for an element, for a center atom, that is located on the 1st energy level, or 1st row of the periodic table, or the 2nd row of the periodic table, because they don't have the d orbitals. That's kind of like a spare bedroom that they use to house more of those electrons. I3 negative, that's an ion. You would write that the exact same way if you're going to draw the structure. It is an expanded octet, and let's look at that one. So again, you may not know that it is an expanded octet until you get started, so let's go ahead and do our happy have for I3. So for happy, I have iodine with like 8, and I have 3 of them. So that's going to be 24 electrons. For have, iodine is a halogen, so it has 3. Now it is I negative, so we are going to include that extra electron in the have only. So that's 21, 22. And when I do happy minus have, I get 2 divided by 2, so I only have 1 bond, and that is impossible to have when I'm trying to bond together 3 things. So that's one of your indications that you do have an expanded octet. So what we're going to do is just take our have and divide it by 2. That tells me how many electron pairs I'm going to have to work with. And then we start linking things up. So iodine is going to bond to iodine, which is going to bond to iodine. Now I have 2 bonds already taken care of, and that'll take 2 of my electron pairs away. So I have 10 electron pairs remaining. Start filling up the ones on the outside. Fill up their octets. All right, and that uses up 6 of those electron pairs. And so I only have 4 more electron pairs to deal with. And so those have to go on the outer, or on that center atom to complete this. And again, because it is an ion, we have to notate that it had an extra electron, so we put it in square brackets with the charge outside of those. Okay, realized a mistake here. 22 divided by 2 is not 12, it is 11. All right. So here we would end up with 9, and then here we would end up with 3. So that guy right there isn't there. All right, so that is our structure for I3. Sorry about the mistake. And always when you're writing Lewis structures, you fill up the octets of the outer atoms first, and then any extra electron pairs have to go on that central atom, and that usually is what ends up giving you that expanded octet, but not always. Okay, you can draw some of these. I have some practice for you in drawing expanded octets or electron deficient molecules. All right. So another exception, and the last exception to the octet rule, are molecules with an odd number of valence electrons. NO2, NO, ClO2. These are going to be atoms that have an odd number of valence electrons. And our model deals on pairs of electrons, and so it doesn't deal with odd numbers. So there's no way we can draw these so that each atom has access to 8 when there are an odd number. So if I take the valence electrons of nitrogen, which are 5, and add them to the valence electrons available for oxygen, which are 6, in total I have 11 valence electrons. This is an odd number, and I would know already that I have an exception to the octet rule. Here are the structures, and as you can see, in this structure right here, nitrogen does not have a complete octet, and if I try and correct that, oxygen doesn't have a complete octet. So there's no real way that I can draw these so that each has access to 8. Generally, this is going to occur with things like nitrogen and phosphorus because they start out with having 5 valence electrons, and that already gives us an odd number.